Okay, so today we're going to be looking at vectors. Just before we get into it, a fairly basic sort of GCSE style question, but you want to give this a go just because it comes up in some of the vector questions that we're going to be looking at. So just pause the video and see if you can find the appropriate numbers in each case, and then unpause when you're ready to get the answer. Okay, so in this case, of course, we're treating AP effectively as if it were length 7, PB effectively length 2. The whole thing we'll just call 9 for now. That is to say, it's not literally length 9, we don't know how long it is, but effectively that's what we're going to do here, so that it's going to help with our calculations, because then when we find the ratios, the actual length is not relevant. So AP over AB, in this case we should have 7 over 9. PB over AB is therefore 2 over 9, and AP to PB we should have 7 over 2. So fairly simple, but we just want to make sure that we've got this down. Okay, so we're going to introduce sort of the fundamentals of vector notation. That is, what are vectors, how do we define them, and how do we refer to them mathematically? What is the technical notation? And there's a few different types of notation, so we just want to cover a few of the basics so that we're familiar with each and the sort of the difference between them. So first off, a vector, simply just drawn on a page, is just an arrow, right? It's an arrow because the line, so I mean this line part, this tells you the length. So that's a key part of a vector, is it has a length. And additionally it has a direction. So it's going sort of up to the right, and of course this is why it's an arrow rather than just a line, because an arrow tells you which way along the line it's going. So you have a length and you have a direction. The length also may be referred to as the magnitude, which is probably the more technical term. Okay, we'll see that far more commonly. Oh, it's just not letting me write the E at the end there, so I'm just going to have to write it down here. The magnitude. Okay. So you've got length and magnitude, length slash magnitude, and you've got direction. Those two things. Okay. In terms of how we can refer to certain vectors, we can give them a name. So, for instance, I could call this vector A. And I can use any typically lowercase letter. Convention is A, B, or C, D, E, F, and so on. However, to distinguish these letters as being vectors rather than, say, just a number, we tend to write it with an arrow on top, or more easily, because when you're doing calculations you want to be able to write things down quickly, just a single line. Okay. Within the textbook, and this is a feature of textbooks, it's written as a normal letter, but then it's written in bold. So this is me here attempting to make it bold. Okay. Obviously, this version you're only going to see in written text, whereas these two you will see in handwriting. So there's a distinction there between handwriting and what's in a textbook, but all three mean exactly the same thing. They mean a vector, and the name of the vector is A, and it's not a number, it's a vector. There's an alternate way to refer to vectors, which is by the endpoints. So if you've got a diagram including many vectors, or some description of a problem that includes vectors, instead of the vector itself you may be told the endpoints, and these are typically denoted with capital letters, capital P for point, and then it tends to go to Q because that's the next letter, again by convention, but you can have any capital letters you like, U, V, W, X, and so on. In this case we refer to the vector simply as capital P, capital Q, again with an arrow on top, and we tend not to do the, sometimes you might see this, I suppose. It's probably acceptable, but I tend not to see it too much, so I would mainly just stick with this. Okay. So those are basically your ways of referring to a vector. Okay, it's effectively a mathematical object which we use to model many things, velocity, accelerations, things in physics, sometimes things in statistics as well, but that's all it is. Think of a vector as a mathematical object with a length and magnitude, and this is how you're going to use your notation to refer to it. Okay, there will of course be specific numbers for each of these properties here, but for the time being this is what I just wanted to clarify. Okay, so then thinking about adding vectors together, so let's say I've got that vector there, let's give it a name, let's call it A, and then let's say I've got the vector B. Okay, so I'm just going to stick with the sort of geometry. If I add two vectors together, I get another vector, and the geometric understanding behind this is simply as follows. Take your vectors, and the order doesn't matter, so let's just write it here, vector A plus B. The order doesn't matter, so let's take that vector A, just do that one first, and then head of the vector to tail, so that is the arrowhead to the tail of the next. We take A, then we'll take B, and I'm trying to sort of copy what I did above, and the result of those two, or resultant is the technical term, is going to be my answer. Okay, so that is the vector A plus the vector B. Okay, so if I just draw it up here again, roughly speaking, okay, that is what I get, that blue vector is what I get when I add the vector A and the vector B together. Okay, so we haven't used any numbers, but there should be a sort of a geometrical understanding here. And if I were to do this in the other order, so let's say I'll do B first and then A. Hopefully you can convince yourself this makes sense in your own notes. So B plus A, let's do B first and then A followed by A, and I'm doing it a bit freehand, so hopefully it's about right. And you can see if I draw now, again, from the start to the end, that there looks pretty much the same as this, and in fact it is the same. Okay, so just like numbers, B plus A in vectors is the same as A plus B. I mean, that's an identity effectively, it's always the case. Okay, so just like numerical addition with vectors, when you add them together, it doesn't matter what order you do them in. And that's the same if you have 2 or 3 or 4 vectors. You're adding them end to tail, you just have a single line at the end. Okay, so no matter how many vectors you're adding up together, you always end up with one vector. And this is how you would do it geometrically. Okay, so let's work through, we're going to work through quite a few examples, and then you'll be able to do some questions yourself. So first off, we've got 3 vectors now. Draw a diagram to illustrate the vector addition. Okay, so this is pretty much what we've just done before, but now we've got 3 vectors. So there's my A, and again notice they're not using any lines or anything on these A, B and C, but they are in bold, and I really want to emphasize at this stage that you want to get in the habit of actually putting the line there. I've actually put that on the bottom, that should have been on the top. So you want to now already start distinguishing your unknown variables, which ones are vectors, which ones are numbers, because it's going to confuse you a lot later if you don't get used to that notation. So you can even just stick with the arrow if you prefer that to remind yourself. So we've got A, I've tried to copy it roughly speaking there, then followed by B, and I need the arrowhead, and then C is sort of straight down, it's about that length. Okay, so this is very approximate. If you were doing it properly, you'd use a ruler or you'd count the squares, but for now I just want you to get the idea behind it. So we get, that is my answer. Okay, that is the vector A plus B plus C. So it's that long and it's going sort of southeast. If you wanted to put an actual number on it, you could, but the way you'd do that would be you'd have to count these squares, and I'm sure you could imagine with a little bit of Pythagoras you could find the length of these various separate vectors, and then if you kind of imagine the grid pattern on this diagram, you could eventually work out the length of that blue one. That's an exercise in itself. We don't necessarily have to do that now, but as long as you can see how you would do it, that's what matters. Okay, so that's it. That's that example done. That's 3 vectors added together. Okay, so now I want to make a point about negative vectors. Okay, so for instance, how would you answer a question like this? A minus b. Well, it's important to remember this is effectively the same as is the case with ordinary numbers. This is effectively a plus the negative of b. Right, it might seem obvious, but it's an important distinction because we haven't defined what it means to take one vector away from another, but we have defined addition. So this thing on the right hand side, it makes sense as long as we can define what this means. What is the negative of a vector? And the way we define that is quite simple. If you have a as being this following vector, let's say that's a. In fact, I'm not going to use the equal sign because that's not really proper notation. Let's just label it. That's my vector a. Then the vector minus a is simply going to be same length, but the exact opposite direction. That's all it means to negate a vector. Okay, I'm not going to write it in words. That's for you to do yourself. It'll take me too long to write out. But you want to note that down, that the negative of a vector, same magnitude, exact opposite direction. Okay, so then since we've now defined that, we can now therefore understand the idea of taking the negative of b and therefore adding or saying vector a minus vector b is the same as just adding the negative of b to a. Okay, so with that said, in theory, if I were to draw 2 random vectors a and b, you should be able to conceptually understand what a minus b is. Probably need to delete that bit, but never mind. So we've got another made up example. There's a, and let's say that's b. And then ask yourself, what does a minus b look like? You can pause the video before I show you if you want. So it's going to be a, and then now take the b, flip it, so we're going to get the negative version. So let's just do it up here. That's the negative of b, and now we're going to add that to the end of my a over here. So roughly speaking, there's my negative b. Okay, and therefore my resultant going all the way from the start to the end is what I'm interested in. That's my a minus b. Okay, hopefully that makes sense. Again, we've not used any numbers. The geometry of how this works is what we want to understand first. Okay, and this idea of the negative of a vector being the opposite direction is very important because you're going to be adding and taking away vectors quite a bit. Okay, and then multiplying vectors by a scalar. In this case, scalar just means an ordinary number, okay, as opposed to a vector. Okay, in other words, not a vector. Okay, because we've got numbers and we've got vectors, and we tend to refer to that as scalars and vectors. So how do I multiply vectors by a scalar? Again, I'm not going to use numbers yet, at least for the vector. I will for the scalar. We want to look at the geometry. So let's draw A. And then what makes sense as a sensible definition? 2 times the vector A, which I've written as 2A. What would that look like? The definition in the context of vectors is same direction, but multiply the magnitude by the scalar. In other words, it's going to be twice as long, same direction. So I'm going to sort of roughly do this by I. That, roughly speaking, is 2A. And then 3A would look like this, and so on. Okay, that's supposed to be 3 times the length there. This is 3 times the length of that one. Okay, and that works for also fractions. So for instance, this would be half a, maybe something like, something like this might be, I'm trying to make these all the same angle, they should be the same angle, all of them. That'd be a quarter a. Okay, and then of course you can multiply by a negative number. Let's start simple first. Minus a, remember that's just the opposite direction. Okay, so that's minus a. And then what about minus 2a? In fact, I'm just going to change this one. So to turn that into minus 2a, it's as simple as, well, if I change the minus here, and then just put the head on the other end. So now it's in the opposite direction. Okay, so I've corrected one of my previous ones. This is minus 2a. Okay, so you've effectively got minus, which can change the direction, and then an additional multiplying factor of a number can change the length. Okay, there's no operation at this stage for changing the direction of a single vector. There are such operations, but they're a lot more advanced. So for now, the geometry that you want to understand is adding them, taking them away from each other, multiplying them by a number, and negating them. Okay, so then one more thing to discuss before we look at a few more examples is the idea of parallel vectors. Now, it should be fairly obvious what parallel vectors are. So, you know, if I just throw up a few examples, these two vectors I've drawn, let's call them A and B. They're clearly parallel, roughly speaking, from, you know, my attempt to draw a straight line. If I do a couple more, these two are parallel, right? The position that the arrow's in doesn't particularly matter, as long as the direction is the same. I'm just going to do one more and just think about, you know, something like, say, a vertical arrow. Let's mix it up a bit, and I'm going to do this. Okay, now are the vector here, let's say the orange pair, I've kind of reused A and B, but let's say the orange A and B on the right, are those parallel? Well, they are, because if you were to convert the vector into a straight line, in each case, you'd have two parallel lines. Okay, this is what it means for a vector to be parallel. So actually, the fact that A and B are in the opposite direction doesn't affect that they're parallel. So they're either the same direction or they're completely in the opposite direction by 180 degrees, then it's still parallel. And additionally, the magnitude or length of the vector makes no difference. It doesn't matter what the length is. So I know, for instance, with the red pair, I kind of made them almost the same length. Likewise for the green. Then for the third example, I made A and B different lengths, but it doesn't matter. So being parallel is all about the direction. It's either the same direction or it's the complete opposite direction. Whereas, you know, a counter example, so let's say not parallel, would be, and then it should be fairly obvious, any two vectors which are not in the same direction or in the perfectly opposite direction. Okay, so that's geometrically what it means for them to be parallel, but then you want to be able to define this mathematically as well. So there's a standard way of doing this, and that's as follows. If you have the vector A and the vector B and they're parallel, that's the same thing as saying, so this means equivalent, to the following mathematical statement. Vector A is equal to lambda times vector B. So this is lambda, the Greek letter lambda, and it's a scalar, right? It's just a number. I don't know what number it is, but it is some number, 1, 2, minus a half, I don't know. And all that's saying effectively is that A and B are the same direction but different lengths. And of course lambda could be positive or it could be negative, which is why when you have two vectors parallel, it doesn't matter if they point the same way or complete opposite direction, but anything other than those two possibilities, and then they're not parallel. So that's how you write it mathematically. So when you get to more advanced vector questions, you want to be very much used to this concept of having one vector equal to lambda times another vector. Okay, and lambda is some number, you don't know what it is. Sometimes it might be necessary to work out what it is, sometimes it won't be. But that is how you mathematically express the statement that A and B are parallel. Okay, if you were then talking about even more vectors, like let's say you wanted to say C and D are parallel, you might use a different lambda. So you'd start having things like lambda 1, lambda 2. But in this case, it's only one pair of vectors. We don't need to worry about that. We just call it lambda. Okay, so you've got examples of the geometric definition of being parallel, and then you've got a mathematical way of writing it. Okay, so now we want to get comfortable with manipulating named vectors and finding multiple representations. So what we have here on the right hand side, we've got a diagram of various vectors going on. So in some sense vectors are just sort of line segments, aren't they? And then you either travel, in this case D is traveling in that direction and minus D is traveling in the opposite direction. Okay, so all of these are vectors going on here in some sense. You've got 1, 2, 3, 4, 5, 6, 7 of them. 4 of them have been named, and they've been named A, B, C, D, and the other 3 just don't have a name. Although you could come up with a name, for instance, this one here, if I were to give that a name, I could use the point notation, couldn't I? I could call it ST. Right. I could also call it TS, which would be the other direction. And those would be two slightly different vectors, just opposite direction. Okay. But you've been given some names for 4 of them in this case. So instead of writing QR, for instance, we can write B. Okay, they're exactly the same thing. In fact, let's just write those there. So QP is the same thing as A. QS is the same thing as C. QR is the same thing as B. And obviously you have to note the direction of the 2 points. You read it left to right. Q goes to R. And then D is RT. Okay, so we just want to get used to these 2 different ways of expressing vectors. Okay, let's look at the actual question. Oh, I've written out what they've already told us. Oh well, never mind. So we've been asked to find, in terms of A, B, C, and D, these various lines on the diagram. I'm just going to do 2 of these, so I don't spend too long on this example. Let's do C first. Okay, so C is PT. So we want to find that vector there in that direction. Okay, that's PT. And the way you're going to answer this question is you basically need to think, okay, I'm going from P, I start at P and I end at T. Is there a way of starting at P and ending at T which follows a path of vectors for which I already have names? So for instance, I could go from P to T straight away, but that doesn't have a name. It doesn't have the name A, B, C, or D, so I can't do it. What if I went from P to S to T? That also goes from P to T, but again, PS does not have a name, ST does not have a name. Right? By a name, I mean A, B, C, or D in this case. So let's pick something that does have names. If we go from P to Q, and then Q to R, and then R to D, that works. R to T, I should say, yeah? Then we go from P to T. So PT is the same thing as, and this is how we'd write it in vector notation, it's the same thing as P to Q plus Q to R, because remember this is what vector addition is, it's putting them head to tail, R to T. And then we can say, well, PQ, I know what that is. Now think carefully before I write it. What is PQ? It's minus A, right? Because I'm traveling along A, but in the opposite direction, we have to take note of that little arrowhead, right? In this case, they've put the arrows in the middle of the line. Sometimes you do that, or sometimes you put it at the end. Doesn't particularly matter, as long as the direction is shown. So that vector A is actually QP, but PQ then is the negative version. Okay, so there's minus A, and then QR, that's just B. RT, that's D, and that's it, you've got the answer. Okay, so PT is minus A plus B plus D, or B plus D minus A. Again, the order doesn't matter. Okay, let's do one more. TS, let's do it in, let's choose purple. So there's TS, which is this here, from T to S. There's my arrow, and then we find a path. So T to S, that's the same thing as going from T to R, R to Q, Q to S. Right, so T to R, R to Q, Q to S. That starts at T, ends at S. I'm just going to write this one straight down. That's equal to minus D, and then minus B, because I'm going against the B direction, and then plus C, and then make clear their vectors. Yeah, okay, that's it. So that's a lot of people seem to struggle with this concept, but hopefully it makes sense to you. You're just finding another path that achieves the same thing. Okay. So with that said about the paths, this is a classic example. It's a very simple example, but it's noted here as being called the parallelogram law. And the idea is, if you've got a parallelogram like this one, then you can actually label two of the sides as two different vectors, and then notice, of course, that because it's a parallelogram, this one, AD, is exactly the same vector as BC, and AB is exactly the same vector as DC. So it's kind of like you're doing B, and then let's label it actually. You've got B, and then this is A, and that's also A over here, and this one's also B. Okay, so you've got each of those two vectors appearing twice. And then it says find AC. Well, it should be fairly clear that in this case, AC is equal to AD plus DC, which is just B plus A. But you could also go the other direction, the other way around on the parallelogram. You could say it's AB plus BC, which is the same as A plus B. Okay, so that's you doing your two options, going that way or going that way, and you're just adding up the two vectors in the usual sense. Okay, so it should be fairly self-explanatory really from what we've seen before, but parallelograms are quite a common feature of vector problems, so I guess it's good to see a specific example of it. Okay, and then our penultimate example, this is to just test that we've understood the definition of parallel vectors. Show that these two vectors are parallel. Okay, now just to clarify what's going on here a little bit, why these things we've been given vectors. Normally we'd say, you know, you've got a vector A, that's one vector, and then you've got a vector B, that's another vector. So why here are we talking about adding and multiplying A and B and getting two different vectors? Effectively, this vector 1 here and this vector 2 here are just an addition and multiplication of two other vectors, A and B. We don't know what they are. It doesn't particularly matter. So imagine there are two vectors out there, A and B, and I multiply A by 6, making it 6 times longer. I multiply B by 8, making it 8 times longer. Then I add those two together, gives me a new vector. That's what this V1 is, what I've called V1, the first vector. And then likewise, this other combination is V2. So prove that those two things are parallel. So apparently it's possible, and it doesn't matter what A and B were in the first place. Okay, and the way we do this is to just think about the definition, right? So I've called them V1 and V2. Remember that V1, V2 being parallel is the same thing as showing that V1 is some number multiplied by V2. So then the question is, can we show that? In this case, what the question is effectively asking you to do is find the lambda value, because if you can find the value, that means you've proven that they're parallel. And if no such value exists, then they're not parallel. So is there a number which I could multiply one of them by to get the other? And in this case, just think about, for instance, just pick one of them, the A's, let's say. Right, so to go from 6 to 9, or likewise from 9 to 6, it doesn't matter which way around, what do I multiply by? Let's go from 9 to 6. So that's times 2/3, right? So then we ask ourselves, okay, is that going to work? 2/3? So now multiply the whole thing by 2/3. 2/3 times 9a plus 12b. Okay, and to do this, we're multiplying the separate components by 2/3. So 2/3 times 9 is 6. 6 lots of a. 12 times 2/3 is 8. And yep, indeed, that is actually equal to V1, right? We've got 6 and we've got 8, which lines up with that 6 and that 8. So if I had gotten, so 6 I was always going to get because I picked 2/3 to make it 6, but I might not have gotten 8. So if I didn't get 8, then they're not parallel. But because I did get 8, they must be parallel. It worked. That number 2/3 worked for both parts. So therefore, they're parallel vectors. Okay. Okay, so final example. So this is going back to the similar problems we had before, where you're just trying to find a different path to achieve the same thing. We also just want to label everything first before we start trying to solve the problem. So you've been given a triangle, 3 points ABC. They've then said AB is equal to A, so I think we should label it as such because it's not on the diagram. So that's A. So A is the red vector, capital P is just a single point. Remember, the capital letters tend to be points. AB is A and AC is B, and it's in that direction. And that's AC, and that we're going to label B. P is the midpoint of AB, so we just need to remember that. Well, P is the midpoint of AB. Right, there's a way we could write that mathematically, actually. So let's do that now. P is the midpoint of AB. Okay, let's think of how to write this mathematically. What does that tell me about the vector AP? Right, think about it. AP. Well, AP is half the length of AB, right? Because it's a midpoint, meaning it's halfway along, right? So that AP distance, same direction, they're parallel. In fact, they're not only parallel, they coincide with each other, right? AP is in the same place as AB, but it's shorter. It's half the length. So that means we could then also just write AP is equal to half AB, which by definition is little a. So this is half little a. Okay. So that's us taking note of that midpoint fact that we were given. And then we were also told that Q divides AC in the ratio 3:2. Okay. Again, let's write that mathematically. So that's the same as saying that AQ is equal to, now it's not a half, AQ is some fraction of AC, right? Because AC goes from A to C, it's the full length, and AQ is just the part way, it's a part way vector. It's in the same direction, but it's shorter. So it's going to be some fraction times AC. Think about what it would be. So this goes back to that starter question really. So if these are in the ratio 3:2, 3 plus 2 is 5 3/5. Okay, you just have to remind yourself of ratios if you can't remember how to get that. Okay, so AQ is 3/5 of AC. And then again, because AC is defined as little b, we can write this as 3/5 little b. Okay, AC and B are exactly the capital AC and little b are exactly the same thing. Right, so now we can write in terms of A and B these various things. Again, I might even just do one of them. What might be a tricky one? Let's just go straight for D. Okay, so we're going to do PQ in terms of A and B. So this is where you really want to just be good at writing things in the notation, because if you get used to the notation, sometimes the answer will just fall out of your working. So PQ is this. I want that. Okay, from P to Q, and we need to think, right, what things do I already know, and I want to follow that path. So how do I get from P to Q, going along what I know? So I already know what I know AP, which means I also know PA. It's just a negative. I also know AQ. So if I go from P to A and then to Q, I'm following stuff that I know. Right, I'm following a path with known values. So let's do it that way. Okay, and that should give us our answer. PQ is the same as going from P to A and then going from A to Q. Now P to A, remember we've got AP here, and AP we said was a half of little a. So then PA is minus that, because it's just the opposite direction. And then likewise, we've got AQ, which is 3/5 of little b. In this case, we don't need to go in the opposite direction. We put it straight in. And that's it. That should be our answer. Right, we've done it. We have written PQ in terms of little a and little b, and it's that. Okay. So I suppose the reasoning for why we're even doing this in the first place, it becomes clearer as you start solving particular problems, but it's all vectors at this stage is all about expressing certain pathways in multiple ways. It's basically a way of talking about, you know, line segments in terms of unknown quantities. So now at this stage, if you suddenly knew what little a and little b were, you could very quickly get an expression for PQ. So you've almost done all the working without knowing any of the numbers, and that would be a lot harder to do if you didn't have a system of notation for doing it. Okay, so I'm going to give you some questions to try now. Let's take a look at how many I've found. So I have 2 pages. Okay, so try the questions. You can pause the video. In terms of getting the answers, I've noted you can find them in the textbook, which you should have. Not at home, then find it online digitally. It might be a bit annoying, you know, the first time, but you'll get used to it. It's very easy to just look it up at the back. So this is just telling me it's in the Pure 1 book. Just look up chapter 11a, question 4. This one's chapter 11a, question 8. Yeah, so it should be easy to look up the answer, but obviously do that once you've tried it yourself. So have a go at these. When you're ready, you can pause the video now. And then let's just look at the second page. And you can also have a go at these 2 questions as well.